Okay, welcome to AQA AS Chemistry, Paper 1, Inorganic and Physical Chemistry. This is the 2021 paper 7404/1. Let's get into it. As we go through the walkthrough, try the questions, pause the video, then look at the explanations. Okay, question 1. This question is about atomic structure. You can see 1.1 here in figure 1 is a model proposed by Rutherford to show the structure of the atom. We've got the positive nucleus surrounded by electrons. State 2 features of the current model not shown in this Rutherford model. So obviously the first thing we can't see is the protons or neutrons in the nucleus. We also see 3 electrons in a single orbital. Well, we now know in the current model that electrons occupy different energy levels or different orbitals or different energy shells. Okay, moving on to question 2. Actually, question 1.2. A sample of tin is analysed in a time-of-flight mass spectrometer. The sample is ionised by electron impact to form +1 ions. Table 1 shows the data about the 4 peaks in the spectrum, MZ112, and so forth. You can see we've got the percentage abundance for all the different MZ ratios except for the one at 120. The question is, give us the symbol, including the mass number of the ion that reaches the detector first. Then calculate the relative atomic mass of tin in the sample. Give your answer to 1 decimal place. So which of these ions would reach the detector first? Well, it's the ion with an MZ ratio of 112 because the MZ ratio is equal to the atomic mass of the element. It's a positive ion, so we need to include the plus sign. Probably a mistake a lot of people make. They're always going to have a charge, the ions in a mass spectrometer. Now we need to work out the percentage abundance that's still to be determined. So we do the total percentage abundance, which we can assume is 100, minus the sum of the other 3 potential abundances, and that will give us the 4th one that we've yet to determine. And the answer is 30.84%. Right, now we need to calculate the relative atomic mass. So how do we do that? This is a GCSE level question. So we need to times the MZ ratio by the percentage abundance, and work out the sum of all of those and divide it by the total abundance, which is 100. The only difference with a GCSE question here is instead of MZ ratio, it would say mass, whereas we can assume the MZ ratio is equal to the mass, so it's the same kind of thing. We're going to divide that by 100, and then for the 4th mark, we need to make sure that this is to 1 decimal place. And if we pop this all in the calculator, we're going to get an answer roughly, when it's rounded up, as 116.5. So let's divide that by 100, like so, and then we get 116.5. Now let's look at question 2. This question is about magnesium and its compounds. State 1 observation when magnesium reacts with steam. Give an equation including the state symbols for this reaction. Well, a clear observation when you react magnesium is that it gives off a bright white light, and you'll probably remember that from GCSE, burning magnesium in a Bunsen burner. Now, the product form will be magnesium oxide, and that is a white solid or a grey solid or a grey ash or a white ash. Now, when we write the equation, magnesium is obviously a metal and it's solid at room temperature, so the state symbol is S. Now, for water, you'd think it's liquid, so it would be L, but this is steam. So let's remember that it's in the gaseous state. And it's going to form magnesium oxide. And like all the group 1, 2, and 3 compounds, it's going to be like a white solid. And it gives off hydrogen gas. Okay, 2.2. Describe the bonding in magnesium. Now, there's 3 types of bonding. You should know these off by heart: covalent, ionic, and metallic. Of course, magnesium is a metal found on the left of the periodic table, so it has metallic bonding. We need to describe that metallic bonding. So we've got magnesium's a group 2 ion, so it has +2 positive charge each ion, and it has delocalized electrons, 2 for each ion. The actual metallic bonding is the force of electrostatic attraction between the delocalized electrons and the positive metal ions. You can, in AQA, get away with saying attraction between positive metal ions and delocalized electrons, or between the Mg2 plus and the delocalized electrons. But make sure you don't use a GCSE term like free electrons. You can't use that at A level. Right, let's move on to 2.3. Explain in terms of structure and bonding why magnesium chloride has a high melting point. We need to pay careful attention here to the question. It says structure and bonding, and it's for 3 marks. So if you just state the structure and the bonding, you're going to pick up 2 of those. Magnesium chloride, that's a metal and non-metal, so it's ionic. And the structure of all ionic substances is giant. So it has a giant structure and it has ionic bonds. Now we need to describe the ionic bond. Well, there's lots of strong ionic bonds which need lots of energy to break. And those strong ionic bonds are made of electrostatic forces of attraction between positive and negative ions, and they require lots of energy to break, hence the high melting point. Magnesium 2 plus and Cl minus ions, you can say instead. Give one medical use for magnesium hydroxide. Now, you should know by now hydroxides, which can release the OH minus ion, are bases or alkalis, so they neutralize acids. So it's for neutralizing stomach acid, or indigestion, or reflux, or use as an antacid, not spelled like that. Yeah. It's called milk of magnesia as well. And an unusual use is as a laxative, which relieves constipation. Oh, a bit grimy, but here we go. Okay, so hope you're all good so far. If you like what you're getting so far, just subscribe, hit the like and all that business. All right, let's move on. And if you've got any comments or questions, please put them in the comments. Right, the question is about redox reactions. This is question 3. State in terms of electrons the meaning of the term oxidizing agent. Now, oxidation is loss of electrons and reduction is gain. You might remember oil rig is a good way of remembering that. Oxidizing agents accept electrons. They get reduced themselves, so they gain electrons. But of course, they cause something else to be oxidized. They cause something else to lose electrons. That's why they're called oxidizing agents. Now, if we look at 3.2, it says we've got Cr2O72 minus, and this can be this can oxidize SO32 minus in acidic conditions, which mean there's hydrogen ions knocking about, to form Cr3 plus and SO42 minus. Deduce a half equation for the oxidation of SO32 minus to SO42 minus. Deduce a half equation for the reaction of Cr2O72 minus to Cr3 plus. Deduce the overall equation from the oxidation of SO32 minus by Cr2O72 minus. So we want to start with this half equation by writing SO32 minus. And then what you do with these ionic equations, you just draw an arrow to go to the other side and write the known product on the other side, which is SO42 minus. Now we can work the rest out. We can see that we're an oxygen atom light on the left-hand side. So we've only got 3 on the left and 4 on the right. So where can we get another oxygen from? Well, we can get this from water. So in these half equations, when you're missing oxygen on one side, make up for it by adding a water molecule. So let's go ahead and put that water molecule in here. Now, that's presented us with a new problem. We've got hydrogen ions on the left and not on the right. So what we need to go ahead and do now is add 2 hydrogen ions to the right. And we got a clue with that in the question when they mention acidic conditions. So we're going to have 2 of these H plus ions. Need to put a little 2 here. And that's all balanced up. Now, you can also see that the electric charges must balance on either side. It's a good way to check you've got the equation right. So we should have -2 on each side. Now, we can see that with those hydrogen ions, we wouldn't get -2. So we need to add 2 negative electrons. And that means that now we've got -2 on each side of the equation. It's now electrically balanced. So use those electrons to make sure the charges balance on both sides. Now, for this half equation, we write down Cr2O72 minus. We go again and put the arrow in the middle. We write Cr3 plus on the right-hand side. Now we go back to the left and we say, hold on a minute. We've got 2 Crs, so we need to double the Cr3s on the right. Like so, big 2 coefficient there. Now we say, look, we've got 7 oxygens. Do you remember the trick? If you've got oxygens on one side but not on the other, you need to add water in like we did above. So how many oxygens would give how many water molecules will give us 7 oxygens? We're going to need to add 7 H2Os on the right. And that will make up for those 7 oxygens on the left. There you go. We've now got the problem of having 14 hydrogens. We need to add those over on the left. 7 times H2. So let's add those in here if I can manage to squeeze that in. Oh, I've not done a good job there. I'm not going to be able to get the 14 in. Let me just correct that. Now we need to make sure the charge is balanced. We're going to add these 14 hydrogens here. And 14 hydrogens with the -2 on the chromate is going to give us +12. You can see on the right, we've got 2Cr3 plus is +6. So in order to bring the left hand down to +6, we can add 6 electrons to this left-hand side, negative electrons, and that's going to bring it down so that we have a +6 charge on both sides of the equation. So once you've written out your half equation, just the final thing is to ensure the charge is balanced. There we go. Now they're going to balance. Have a look there. Great. Now we need to do the overall equation. And how you do the overall equation is you look at the electrons in each half equation and you multiply one of them, or both of them in some situations, so that we get to, so they balance basically. And here, if we just do 3 times the top equation, we're going to get 6 electrons, and that is going to balance both equations. So now you write everything down with the new 3 times multiple on the reactants and products at the top. And then all of the cases left to do once we write this down is to write down the hydrogen ions, which are going to appear on both sides of the equation, and the water molecules, which will appear on both sides, and the electrons, cancel them all out. And there'll be 6 electrons on each side, so they cancel 7 waters on the right, and there'll be 3 waters on the left, so we only need 4 waters on the right now. And we had 14 hydrogen on the left, and we had 2 hydrogen on the right. No, we had 6 hydrogen on the right, so we only need 8 on the left now, as was shown earlier. Beautiful. That's all balanced once you've cancelled everything out. Okay, let's move on to question 4. This question is about the identification of ions in unknown solutions. The student completes a number of test tube reactions on solutions A, B, and C. Table 2 shows the student's observations. 4.1. Suggest the identity of the positive ion in solution A. Give the simplest ionic equation for the formation of the white precipitate in test 1 for solution A. So if we have a look here, the identity of the positive ion in solution A, well, we look at the 3 tests. 3 tests have been done on solution A. There's been nothing happening when they were reacted with warm sodium hydroxide or with acidified silver nitrate. But when they reacted solution A with sulfuric acid, we got a white precipitate. And this tells us that we've got barium ions knocking about, because that white precipitate is barium sulfate. So we want to do Ba2 plus SO4 minus, and this goes to BaSO4. Now, ions would always be in AQ, and barium sulfate is insoluble, hence why we use it for things like X-rays and medical imaging. So it's going to be a solid symbol. Okay, let's look at 4.2. Different gases are formed when solution B reacts in test 1 and 2. Suggest the identity of each gas. Give the simplest ionic equation for the formation of the gas in test 2. Okay, so the gas formed in test 1, we can see it effervesces. So that's going to be carbon dioxide. If you add an acid to something and carbon dioxide comes off, it's likely to be a carbonate. We've got carbon dioxide coming off there. And then in test 2, we get red litmus paper turns blue. That's going to be ammonia. That's a good sign that we've got ammonium ions knocking about. So for the equation, we want to write ammonium ions plus hydroxide. And this is going to release the ammonia gas, which we tested for and turned our litmus paper blue. It's going to release water as well. Super duper duper. Okay, we're going to move on to question 5 now. Actually, sorry, scratch that, 4.3. The student thinks the solution C contains either chloride ions or bromide ions. Describe a further test or test to show whether solution C contains chloride ions or bromide ions. Now, chloride ions give you a nice white precipitate. Bromide ions give you a green precipitate with acidified silver nitrate. The issue here is that you could confuse easily between white and cream. So what we do is we add dilute ammonia solution. If the precipitate dissolves, then it contains chloride ions. If the precipitate doesn't dissolve, then it's bromide ions. So that's a good way to distinguish between these quite similar colors or quite similar precipitates. The white and the cream is quite qualitative to distinguish between them. So if you ever get stuck wondering, is that white, is that cream, add dilute ammonia solution. If it dissolves, it's chloride ions. If it doesn't dissolve, that tells you you've got the bromide ions. Okay, let's move on. Right, we're up to question 5. This question is about chlorine. So 5.1, chlorine has a low boiling point because the forces between the molecules are weak. Explain how these forces arise between the molecules of chlorine. So what we want to look at here is chlorine molecules. Why do we actually get these weak intermolecular forces between chlorine molecules? Well, let's draw some chlorine molecules out here. So here are 2, yet 3 chlorine molecules. And what you can see here is that I'm just putting these pink dots on. These are like electrons buzzing around. Now, electrons randomly move about, and if by just random chance there are more electrons on the right-hand side of this non-polar bond, then it will become delta negative and delta positive. It will have a temporary dipole. What will happen is the chlorine, which is negative and has slightly more electrons, will repel the electrons from the nearest chlorine of the adjacent molecule. And that will become delta positive and delta negative and so forth. So what we say is a temporary dipole forms in the first chlorine molecule due to the random movement of electrons. This induces a dipole in the adjacent molecule, and so forth, and on and on and on, forming these weak intermolecular forces. So it's really this imbalance of electron density or a temporary dipole. So as you can see here, what I'm writing here, the random movements of the electrons form either a temporary dipole, or you can say an imbalance in electron density. This then induces a dipole in the next molecule. And those 2 temporary dipole molecules with temporary dipoles are now attracted to each other. You can see by my green dotted line. And there you go. It's like a domino effect. Okay, let's move on. (5.2). Give an equation for the reaction of chlorine with water. Give a reason why chlorine is added to drinking water. So we want to do Cl2 here, obviously, chlorine, and H2O, which is water. Chlorine's a liquid. Chlorine's a gas, sorry. Water's a liquid. Anyway, they're going to form hydrogen chlorate, or hydrochloric acid, sorry, and hydrogen chlorate. Now, this is a reversible reaction. Why do we add chlorine to water? It's because it kills the bacteria. It's basically going to kill microbes or pathogens in the water. You could say it's going to sterilize the water. Okay, chlorine reacts with cold aqueous sodium hydroxide in the manufacture of bleach. Give the equation. So this is slightly different. Cl2 plus NaOH. And this goes to sodium chlorate, NaClO, and it's sodium chlorate 1, NaClO, and that's because the chlorine has a +1 charge. We call it sodium chlorate 1. and sodium chloride and water. Actually, in the old syllabus, you used to have to know that when it reacts with hot sodium hydroxide, it forms sodium chlorate 5 as well. Okay, you don't need to know that anymore. Let's look at question 6. Right, let's do that again. So calcium sulfide reacts with calcium sulfate as shown. Calcium sulfide here plus calcium sulfate goes to calcium oxide and sulfur dioxide. 2.5 grams of calcium sulfide are heated with 9.85 grams of calcium sulfate until there is no further reaction. Show the calcium sulfate is the limiting reagent in this reaction. Calculate the mass in grams of the sulfur dioxide formed. So first thing we need to do is work out the moles of calcium sulfide that we have. And we know the calcium sulfate is limiting. So let's do 2.5 grams over 72.2 mR. And we're going to get the moles of calcium sulfide. And that is 0.0346. It's always good to write down and label the calculation you've done, like I've done here. Now, we know that this is a 1 to 3 from the coefficient in the equation. It's a 1 to 3 reaction. We can see that from the coefficient in the balanced equation. So I need to make 3 times that amount of moles. I should be making 0.0346 times 3. And that is 0.103 moles or 0.1038 moles. Now, obviously, I'm not making that much because it tells us it's limiting. So how much do I actually make? Let's check it out. We've got 9.85 grams of calcium sulfate. So that's the limiting reactant. Let's see the actual moles of calcium sulfate that we have. And the actual moles is 9.85 divided by the MR of calcium sulfate, which is 136.2. We'll see here that I've only got 0.0723 moles. So I'm short by kind of a third there. I'm missing quite a chunk, or a quarter. I'm missing quite a chunk of the moles that I needed. So we can see there that that is the limiting reaction because it's less than the required amount. Okay. Let's now look at the next part of the question, which was calculate the amount of sulfur dioxide formed. Well, we can't use the calcium sulfide here. We have to use the sulfate because that's the limiting reaction. So you've got to use the limiting reactant to calculate how much product you make. And we can see that the ratio of calcium sulfate to sulfur dioxide is a ratio of 3 to 4. Okay, so we can see that is 3 to 4. Well, what you need to do then is times these moles by 4 over 3, 0.0723 by 4 over 3, and that will give you the moles of sulfur dioxide created, and that is 0.096 of sulfur dioxide. And we need to know the mass of sulfur dioxide, so we're going to times it by the MR of 64.1, which is what you get when you add sulfur and oxygen, or sulfur and O2 together. We're going to get 6.18 grams. And that's that question wrapped up. Hopefully, you did pretty well there. Okay, let's go to question 7. Only 3 more of the main exam to do. This question is about combustion. State the meaning of the term standard enthalpy of combustion. So the enthalpy change when 1 mole of a substance completely burns in oxygen. And hopefully we're going to write under standard conditions. Okay, let's look at 7.2. A student does an experiment to determine the enthalpy of combustion of propan-1-ol with an MR of 60. Combustion of 0.497 grams of propan-1-ol increases the temperature of the water of 150 grams of water from 21.2 degrees to 35.1 degrees. Calculate a value in kilojoule per mole for the enthalpy of combustion of propan-1-ol in this experiment. The specific heat capacity of water is 4.18 joules. Let's get to it. Q equals mc delta T. So we know that the mass is 150 grams. We know that the specific heat capacity is 4.18, and we know that the temperature change, delta T, is 13.9. whack them all together, and we get 8,715.3 joules. Now, the answer is in kilojoules per mole, so we need to convert those joules into kilojoules. So we divide that by 1,000, because if you look down below, you can see it's kilojoules per mole. And so then we're going to get 8.715 kilojoules are given off in this reaction. Now we need to do it per mole. That mole to the -1 means divide by. So we're going to divide by the moles. So what is N here? Well, we'll be given the MR is 60, and we'll be given 0.497 as the mass. You should know your GCSE equation, mass over MR equals moles. So 0.497 over 60 as the MR of propan 1-ol, and that gives us our moles, 0.0083 moles. Divide the kilojoules by the moles to get kilojoules per mole. Pop that in the calculator. You should get 1050, 1050 kilojoules per mole. Now that's going to be exothermic, so there should be a negative symbol on that. Sometimes they'll deduct a mark if you don't put a negative symbol on that. All combustion reactions will be negative. 7.3, the enthalpy of combustion determined experimentally is less exothermic than calculated using enthalpies of formation. Give one possible reason other than heat loss. So this is very faint, hasn't come out very dark at all. But imagine you're heating up some water here. Obviously, you've got a thermometer in there. You need to measure the temperature change. That's how we calculate our joules. However, we're losing a lot of the heat. So this would be a reason why we get a less exothermic reaction. But it says other than heat loss. What else is the problem? Well, we have fuel in a little spirit burner here. And of course, fuels are volatile. They have low boiling points. That's what volatile means. So they evaporate. So that's one of the problems, is the evaporation of fuels. Another possible problem here is incomplete combustion. Normally, when we do complete combustion, we get carbon dioxide and water when we burn a fuel. But if you get carbon monoxide, you get less heat. And you've all seen that with the orange Bunsen burner flame, which isn't complete combustion. And it's at a lower temperature than that roaring blue flame on your Bunsen burner, where you get complete combustion. Right, let's look at question 8. A student is provided with 5.60 grams of ethanoic acid contaminated with sodium ethanoate, CH3COONA. The student dissolves the sample in deionized water and makes the volume up to 200 centimeters. So we've got 200 centimeters of this contaminated mixture. The student removes 25 centimeter samples. What we've done here, I always make a note when this happens, this is divided by 8. We've divided the amount of moles in that sample by 8. The solution, is then titrated with 0.350 moles per decimeter of sodium hydroxide solution. That's our known concentration in the titration. So we know that. Now we need to find out the volume of sodium hydroxide, because we can use that with the concentration to find out the moles. Let's get rid of the rough titrations first. You don't really need the rough titration. They're just something people put in the table. Let's get rid of that first. And the first step here, we're going to calculate the mean titra for 1 mark. So get rid of the roughs. We're looking at the final titra volumes here at the bottom. And we only want to use concordant results. So 20.50 is not concordant, but 20.25 and 20.30 are concordant. So we add these together and we divide them by 2. And that gives us our mean titra, or mean volume of sodium hydroxide solution. Now we need to use this mean to calculate the percentage by mass of sodium ethanoate, the contaminate that's in the original sample. So our first step here is to work out the moles of sodium hydroxide, because we know its concentration. So we're going to do N over C times V. Let's find out the moles of sodium hydroxide. So 0.350 mole per decimeter. And let's multiply that by 0.020275. And that is decimeters. That's the volume of sodium hydroxide. And of course, we had to divide by 1,000 to get that. You should know that off by heart by now. And now we've got our moles, which is 0.0071 moles of sodium hydroxide. Now, this is a one-to-one reaction. How do I know that without writing out the balanced equation? Well, if you look at ethanoic acid, CH3COOH, there's one H at the back of it there. And that's going to react with my OH on the sodium hydroxide to form water in a neutralization reaction. So you can kind of see this is 1-to-1. The OH over here is going to react with this H to make water when they react. And so it's a 1-to-1 reaction. So this means we actually have 0.0071 moles of the ethanoic acid as well, as it's 1-to-1. But that's in the 25 centimeter cube sample we took of the ethanoic acid out of our 200. So we need to multiply that back to find out how many moles of ethanoic acid were in the original 200 centimeters that contained our 5.6 grams. So we need to times it by 8, and that gives us 0.0568 moles of ethanoic acid in the original 200 centimeters. Now we just need to find out how many grams of ethanoic acid that is. So if we've got the moles, how do we work out mass? Well, you know mass over moles and MR. So we can just do 0.0568, which is the moles of ethanoic acid. Or we can do the that times by the MR of ethanoic acid. Now the MR of ethanoic acid, so we want to do, what's the MR of ethanoic acid? 32, 24, 3, blah, it's 60. So 0.0568 times 60, we've got 3.408 grams of ethanoic acid. And that was in our original sample. Now, of course, the original mixture was 5.6 grams. So how many grams of the contaminant of the sodium ethanoate are in the original? Well, now we can just do 5.6, get rid of the ethanoic acid, and we're left over with our contaminating sodium ethanoate. And it's 2.192 grams. Now, the final answer is to work out the percentage of that sodium ethanoate in the original. So we want to do 2.192 grams of sodium ethanoate over the original 5.6 and times 100. And that will give us our final answer for a whopping 6 marks. We're working out the percentage by mass. So 2.192 divided by 5.60 times 100, what's that? 39.14%. Voila. Okay, let's look at 8.2. The student rinses the burette with deionized water before filling with a sodium hydroxide solution. Naughty, naughty, they should have rinsed with the same concentration of sodium hydroxide. What's the effect to the titre? Well, obviously, it's going to dilute the sodium hydroxide that you're putting in the burette. And if it's diluted, you're going to need more of it to neutralize the acid. So it's going to increase your titra. So your mean titra is going to go up. Moving on. Right, let's look at question 9. We're nearly there. 2 more big questions, 9 and 10, and then we're on to the multiple choice. Hydrogen can be prepared on an industrial scale using the reversible reaction between methane and steam. The reaction is done at a temperature of 800 degrees and a low pressure of 300,000 pascals in the presence of a nickel catalyst. You can see from the enthalpy change, it's an endothermic reaction. Explain in terms of the equilibrium, yield and cost why these conditions are used. So really the first thing to notice is that it's an endothermic reaction. In the forwards direction, it's a reversible reaction, so it's going to be endothermic in one direction and exo in the other. We can also see there's 2 gas molecules on the left. There's the methane and the water. And then on the right, we've got 1 carbon monoxide and 3 hydrogens. So we've got 4 gas molecules on the right, and we're going to need that when we come to talk about the pressure. And we have a nickel catalyst. So we'll kind of it's kind of 2 marks for the temp, 2 marks for the pressure, and 2 marks for the catalyst. So let's get into it. A high temperature of 800 degrees is going to cause the equilibrium to shift in the forwards direction, to go to the endothermic side. Because obviously with Le Chatelier's principle, it wants to counter the changing conditions. And so we're going to get a higher yield. So high temperature results in a higher yield. Because it's an endothermic reaction, it's going to try and counter that change. Now, the cost, there's some cost implication when you use a high temperature. It's going to cost you money. So too high temperature is going to cost a lot of money. So that's the cost implication of a higher temperature. Obviously, if you wanted to comment on reaction rate, you probably wouldn't pick up any marks here because it's not what the question is asking, but a higher rate of reaction as well is obviously good on an industrial scale than a slow rate of reaction, and you'll get a high rate always with a high temperature. Okay, kind of waffling on here. We've already scored our 2 marks where I put those green arrows, so let's move on. Pressure. Right, if we use a low pressure, it's going to force this reaction to shift, or force the equilibrium to shift in the direction of the most gas molecules, which is the right-hand side, the forwards direction, which gives us a high yield. So we've used the comparatively low pressure. I think the pressure was 300 kilopascals, only like 3 times atmospheric pressure. So this is going to force the reaction to the right, where we're going to get a higher yield of hydrogen as it tries to counter the change. Why does it go to the right? So you're going to get a mark for saying there's more gas molecules on the right, so a low pressure shifts the equilibrium to the right. Now, a low pressure also saves on cost. Remember, we have to talk about cost with each of these. So the low pressure saves on cost because you need less safety equipment, less goggles, less helmets, less thick steel reaction vessel walls. So you're doing this in massive vats. You might be making all of this in big reaction systems, and you need very thick steel walls to stop explosions when you have high pressure. You don't have to spend your money on that when you're using a low pressure. Okay, the final thing, we're using a nickel catalyst. Now, they have no effect on the position of equilibrium or the yield. However, they do make you reach equilibrium faster, but more importantly, they lower the activation energy for the reaction, which means we can use a lower temperature and therefore save on cost. So the 2 really marks for the nickel catalyst is there's no effect on the yield, doesn't shift the equilibrium, doesn't have an effect on the equilibrium. However, because it lowers activation energy, it will enable you to use a lower temperature. Now, I've waffled on and on there, and you don't need half of that, but there we go. Okay, here we go. Question 10. Sulfur dioxide reacts with oxygen to form sulfur trioxide in an exothermic reaction minus 196 kilojoule per mole. Give the expression for the equilibrium constant Kc for this reaction. So you should know for these expressions, you want to do the products over the top of the reactants. So our products here are SO3, sulfur trioxide. So SO3, we put square brackets, which means concentration in mole per dm. Got a little 2 outside. And then underneath, we're going to put SO2, square brackets, and a little 2 outside because the coefficient's 2, so it's to the power of 2. And then the oxygen has no coefficient in front of it, so we don't write it to the power of anything. And that's our expression. 10.2, a mixture of sulfur dioxide and oxygen is allowed to reach equilibrium in a container with a volume of 1800 centimeters at temperature T. At equilibrium, the mixture contains 0.176 moles of sulfur dioxide and 0.461 moles of sulfur trioxide. At temperature T, the equilibrium constant is 15. Calculate the amount in moles of oxygen at equilibrium. So what we need to do here is, first of all, score our first mark by just substituting numbers in. Nice and easy. Out of 3 marks, you can grab one here by just whacking the numbers in. But remember that we've been given the volume here, so we need to divide our concentration by, we've been given moles here. So in order to find the concentration of each of these substances, we need to divide them by the volume. Moles over volume is concentration. So I'm putting 1.8. I'm converting the 1800 centimeters to 1.8 decimeters. And there we go, 1 mark, beautiful. Now we can rearrange this to find the concentration of oxygen by swapping the 15 and the O2 around, like so. And now the oxygen comes out here, and the 15 goes under there. Okay, plug all of this into the calculator, carefully, using brackets, and you'll get the concentration of oxygen. And the concentration of oxygen is 0.457, and that's mole per dm to the -3. Now, the question actually asked for moles. Look down below. It says amount of oxygen mole, not dm3. We need to get rid of the volume. And as that's moles over volume, we're going to times it by the volume, which was 1.8. If you times it by the volume, you get rid of the volume and you're left with the moles, which is 0.823. Okay, let's go on to 10.3. At a different temperature, a mixture contains 0.025 moles of sulfur dioxide, 0.049 moles of oxygen, and 0.034 moles of sulfur trioxide. Total pressure of the mixture is in a 3,500 centimeter reaction vessel is 255 kPa. Use the data to calculate the temperature in degrees of the mixture. Ideal gas constant 8.31. So we're going to use the ideal gas equation here, rearrange it to isolate T, the temperature. You do that by dividing PV by NR, then you move those out of the way. And it's literally, these are 3 marks, I think, of these. These are just straight conversions. So what's the pressure? Well, pressure should be in pascals, not kilopascals, so 255,000. Then we need to straight convert the volume. Volume needs to be in meters cubed. So we need to go 3,500 and we need to divide it by 1 million centimeters, or 1 times 10 to the 6. And that gives us our volume, which is 0.0035 meter cubed. Now we don't need to convert R, it's just 8.31. We need to know the moles. And the moles is going to be the sum of all the moles in the mixture. So add all the moles in the mixture up, and you get 0.108 moles. Plug it all in by doing 255,000 multiplied by 0.0035 meters cubed, which is the volume. Make sure you put brackets for all of this, otherwise it won't come out good in your calculator. And then divide it by the moles, which is 0.108 times by 8.31. Again, you should bracket that. And that's going to equal 994.5 Kelvin. Now what we need to do is subtract 273, because the answer they want in degrees, and that equals 721. We can get rid of the 0.5 because we put it to 3 significant figures, which is kind of standard at A level. And that's a lovely question for picking up marks. Practice, practice, practice is the way that you get good at chemistry A level. Once you've got these techniques down, these are like 3 marks. Okay, we're on to the multiple choice questions now, guys. Only 1 question per answer is allowed. For each answer, completely fill in the circle. What I'm going to do here is use some examples where I get the answer wrong, and I show you how to cross out the answer. And then if you decide that your crossed out answer is actually right, you need to put a circle around it to indicate to the examiner it's right. Don't put ticks or anything like that. If you write and scribble working out, they're not going to mark it. They're literally looking at your answer. Does it have a black circle in it? Is it crossed out, or is it crossed out with a circle, which means you think it is the correct answer? So let's go to 11. In a time of flight mass spectrometer, molecule X is ionized using electron spray ionization. Which is the equation for this ionization? Well, the first 2 equations are attempts at writing electron impact. So those are not right. The reason why D is correct is because all the state symbols are gaseous. So in a mass spectrometer, it's all vaporized. So it needs to be gaseous. And you add the hydrogen ion from the solvent. Right. What is the electron configuration of V2 plus, vanadium 2 plus in the ground state? So let's write out vanadium's electronic configuration. How am I going to do that? You're going to go to your periodic table. You're going to look for vanadium and find that it has 23 electrons. Its atomic number is 23. So let's write out it with 23. 1s2, 2s2, 2p6, 3s2, 3p6. Here's the tricky bit. Remember, when you get to 3p6, the 4s electrons fill next, and then we go to the 3d. And the other trick is, and it'll be 3d3. Now, this has lost 2 electrons. And the other little trick is, although the 4s fills before the 3d, the 4s also empties before the 3d, which is a little bit unusual, but that's the bit you have to remember. 4s fills before the 3d and empties before the 3d. So it's going to lose those 2 electrons from the 4s2, and that's going to leave us with 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. And the answer to that is going to be A. Okay. Moving on, guys. Question 13. Yeah, I was going to do some orbital stuff there, but forget it. Question 13. Which molecule is not able to form a coordinate bond with another species? So to form a coordinate bond, you either need a lone pair or you need to have space in your outer shell to accept a lone pair. If you look at boron, it's got space. It can accept a lone pair. So that can form a coordinate bond. That's not the answer. Let's check out methane. Methane's in group 4. Well, carbon's in group 4, 4 electrons in the outer shell. When it covalently bonds to 4 hydrogen, there is no space to accept any electrons. So our answer here is methane. It's got no lone pairs to donate, and it has no space to accept electrons, in which case it cannot form a coordinate bond. So the answer here is B. Just to show you, for ammonia, which is NH3, ammonia is in group 5, so it has 5 electrons, 3 bonds. That means there's a lone pair, so it can be involved in a coordinate bond. It can donate that pair of electrons. And then if we look at our lovely H2O, water or oxygen, sorry, is in group 6, so it has 6 electrons on the outer shell. 2 of those 6 electrons are bonded, so there are 4 electrons, 2 lone pairs available for coordinating or donating to other species. So there we go. That's why the answer is methane. No room, no lone pairs. Right, which species has a square planar shape? So you should know this off by heart by now. It is XEF4, and this one's in the CGP book and in your textbook at school as well. So yeah, it's got 8 electrons around the central atom because essentially it's like a noble gas. You add that to the 4 bonds, the F4, you divide by 2, it's 6 pairs of electrons, and you need to know this shape off by heart. When you have 6 pairs of electrons and only 4 bonds, it means you've got 2 lone pairs, one above, one below, and then you have a square planar shape around the outside. So square planar it is. Which bond has the most unsymmetrical electron distribution? So this means which one are the electrons pulled? Are they not sitting in the middle of the covalent bond? What you're going to find here is oxygen. I'm writing numbers here. These are the Pauling, on the Pauling scale. Oxygen is one of the most electronegative elements in the periodic table. It's literally only beaten by fluorine in electronegativity. So the answer is going to be A, because you can see the difference is 1.4 between hydrogen and oxygen. If HF bond was there, it would be the most unsymmetrical of electron distribution because it would have a 1.9 difference. Yeah, so all of the others are, there's less of a difference in electronegativity. Okay, 16. Which compound contains a chlorine atom with an oxidation state of +4? Let's look at this first one, KClO4. Potassium always +1, so group 1. Oxygen is always -2 and less bonded with fluorine sometimes. So times by 4, we've got a total negative charge of -8. The potassium's +1, so the chlorine must be +7. That's not our answer because it's not +4. Let's look at B. So B, the carbon has a +4 charge. Each chlorine must therefore be -1 because there's 4 chlorines, and to balance out the +4, they must each be -1. Let's look at answer C. We've got 2 oxygens, and each one is -2 with a total of -4, right? That means the chlorine must be +4. So our answer there is +4, because what you're trying to do here is balance the oxidation states, unless it's an ion. Right, and you look at this final one here. Well, we don't really need to get into that, but the oxygens are -2 each, the fluorine's -1, so -5, so the chlorine's +5. Anyway, the answer is C. Which element is classified as a D block element? Right, look at this incredible grade D GCSE art drawing. Your D block's in the middle here, so it's just look up in your periodic table. It's molybdenum or molybdenum. Can't really pronounce that. Right, next question. Which element in period 3 is the highest melting point? Okay, so aluminium forms 3+ ions, metallic bonds with a 3+ charge, sodium 1+ charge. So we know aluminium is going to be higher than sodium. They're both metallic bonds, but aluminium has more delocalized electrons, stronger forces of attraction. Then we've got sulfur, which is a non-metal, so it's going to have covalent. And we've got silicon, which is a non-metal, so it's going to be covalent. Sulfur's bigger, so you might at first think sulfur, bigger, better. But silicon has that giant macromolecular structure like diamond. It's in group 4 like diamond. So the answer is actually B. Now look, what happens here? I've crossed out D, so that's what you should do if you write an answer and then you think, actually it's not that answer. Okay, 19. Which pair of electrons, these are displacement reactions. Okay, so when mixed, which pair of solutions will make a dark brown solution? Well, we've got sodium fluoride plus chlorine. There's going to be no reaction. Chlorine is less reactive than fluorine. It can't displace the fluorine. And then this one is no reaction. Bromine is less reactive than chlorine, so can't displace the chloride from the sodium. Here, the chlorine is more reactive than bromine, but when you push bromine out, bromine is yellow, or actually it's even orange. Bromine water or bromine solution is orange in color, so that's not brown. And then in this final one, we've got bromine plus sodium iodide. Bromine is more reactive than iodine, so bromine will displace the iodine. And of course, you know from your biology, your starch tests and all that business, iodine is a brown solution when it's in water. Right, let's look at 20. Some solid sodium halides are reactive with concentrated sulfuric acid. Which solid sodium halide does not produce a sulfur-containing gas as one of the products? Well, it's the order of reducing agents with the halide ions. They increase in their ability to reduce as we go down the group. So sodium chloride ions are the worst reducing agents, so they can't produce sulfur-containing gases. Sodium bromide can, sodium iodide can form hydrogen sulfide, and so forth. Right, 21. Which atom has which atom has one more proton and two more neutrons than P3115? Phosphorus, 3115. Okay, well, if it's got one more proton, it's going to have 16 as the atomic number, and two more neutrons put the mass number up to 33. Aha, but we have one more proton as well. So neutrons and protons make up the mass number. We need to increase the top number by 3 and the bottom number by 1. Okay, I have a problem here. There are 2 with 34 and 16, so I've circled both answers. Of course, I'm not sure which one's wrong. Actually, we do know which one's wrong, because if your atomic number changes, so does your elemental symbol. So this has to be sulfur, because sulfur has the atomic number of 16 and phosphorus the atomic number of 15. So what do we do here? We circle. Doesn't have to be in green. I've just done that funkily in green, but you circle your incorrect answer, and that tells the examiner you now want them to accept that one you've circled. All right, 22. What is a use for barium sulfate? Okay, it's C here, basically, guys. It's used in medicine to produce an X-ray image. It's insoluble barium sulfate, and so lines the internal organs, and you get a picture of that organ on the X-ray. Which ion has the largest radius? Negative ions always have the largest radius. So if you have a mixture of positive and negative ions, go for the negative ions. Why? Because they've got extra electrons, so there's more repulsion, more shielding. The outer electrons are pushed further away from the nucleus. And the ion here with the biggest negative charge is O2 minus compared to F minus. So, yeah. Which element has a first ionization energy lower than that of sulfur? So basically, you've got sulfur, which is in, what's that in? Group 6. Okay. As you go across the period, we might think that phosphorus comes just before sulfur, Phosphorus is in group 5, sulfur in group 6. We might think that phosphorus has a lower ionization energy. However, sulfur's got that extra spin pair repulsion that lowers its ionization energy. It's got that extra electron in the orbital. So it suffers from spin pair repulsion, sulfur does. So the answer is not phosphorus. If you were just going on the trend across the period without thinking about the exceptions, you might go for phosphorus, but it's not phosphorus. Okay, so you might say, well, it's oxygen. Oxygen's above sulfur. But of course, ionization energies decrease down the group. So it can't be oxygen because oxygen's above sulfur. So we'd have a higher ionization energy. They decrease down the group, and you'll find selenium in the same group, but selenium is below sulfur. So the answer is D. Let's get rid of that oxygen answer. Okay, last question, 25. The first 7 successive ionization energies for element Z are shown. Y-axis, we have ionization energy, and on the x-axis, we have the ionization number. Notice a huge jump when removing the 5th electron, or the jump between the 4th and 5th ionization energies. This tells us we're looking at a group 4 element as a big jump in the 5th ionization energy, so we're breaking into a new shell after the first 4. So we might immediately put carbon as the answer. When we look a little bit closer, carbon has 6 electrons, and our graph has 7. So it can be in carbon's group, but not carbon. So the answer is actually silicon, as silicon has more than 7 electrons. It can't be nitrogen or phosphorus, as they're both in group 5, so we get a jump between the 5th and 6th ionization energy. And that's that. I hope that helped, guys. If you like the walkthrough, hit subscribe, hit the like, and check out the other videos.